Hello friends, I welcome you all on India's largest live learning educational platform, that is Gradeup. All the candidates who are joining me, just quickly confirm whether my audio and visual quality, everything is clear so that we can proceed. Everybody just confirm whether my audio and visual quality, everything is clear. Till you report me this, let me just brief you about the session detail, what we are going to achieve in this particular session. You all must be aware that daily at 9 p.m. in the evening, we are discussing the last phase of revision for your important complex concepts of your core subjects like electrical machines. We have discussed almost 9 lectures in this series. 9 lectures we have completed, and today it is going to be the 10th lecture. And today we are going to discuss the crux of voltage regulation and efficiency of the transformer. I hope you all are okay with this and we can proceed, and you all are going to follow the session. But before we proceed, you all please follow the LSS method. That is, you have to like the session, share it with your friends and colleagues in social media so that maximum people can be benefited. And if you have not subscribed to the Gradeup Gate channel till now, please subscribe to the Gradeup Gate YouTube channel. Some of you may be joining me for the first time, so there is my brief introduction. My name is Ashutosh, as you can see on your screen, and this is my brief profile. Before I start the session, again a very important information for all of you. Friends, now you can interact with your favorite faculties directly, and the Gradeup is providing you one-stop platform for this as a Telegram group whose name is Gradeup EC and Electrical Discussion. All the candidates who have not joined this group, quickly join the session. Sometimes you may not be having doubts, but other candidates are having doubts, and those doubts are going to be relayed to you. Apart from this, whatever sessions we are taking on YouTube, Gradeup Gate channel, all those sessions PDFs are going to be available in this Telegram group. So if you join this, definitely you will get a boost up to your preparation. Let us start with the voltage regulation. When I say voltage regulation, you have to understand voltage regulation of the transformer. You have to understand that why we are interested in this parameter, that is voltage regulation. Suppose you are manufacturing the transformer. What you are going to do with your transformer? Finally, you are going to give your transformer to the utility, because utility is going to use that transformer, for example, for power transmission or distribution. It means at the end of the day, you are going to give this finally to your consumer or to the system. Now in the system, our system, or at the consumer level, the voltage profile defines the quality of power supply. If you are getting a low voltage in your house, definitely you will make a call to the utility that why I am getting a low voltage. So voltage profile actually defines, and a very important parameter to define the quality of power supply you are getting in your homes. It means if you take the most simplistic understanding of the voltage regulation, suppose you have a transformer like this. The primary side of the transformer, you are going to connect the voltage source or the generator, okay, and the secondary side you are going to connect the load. Now this load end, who is sitting? Consumer is sitting at the load end. Now suppose we're applying some voltage V1 at the primary side where source is connected. Okay, let me just hide my image. And suppose you are getting a voltage V2. Now, if you are sitting at this consumer end, you tell me what is going to be your expectation. Your expectation is going to be that this V2 should be as close to the rated voltage as possible. Yes or no? Then only you are going to say that the quality of power supply is good. Now what is happening? This terminal voltage is definitely going to depend upon how much load you are applying. This is not going to be a constant voltage throughout the load variation. Now what is the maximum variation in the load? The load you can vary from no load to full load. This is the maximum range in which you can vary the load. It means if you are able to tell your consumer that the secondary terminal voltage is going to vary from V no load to V full load as a ratio of V full load, it means you are going to give the maximum buffer to the consumer that whatever load you are going to connect, the voltage at the secondary terminal is not going to change beyond this. This is the maximum possible change. And this is the background story of how we are defining the voltage regulation of the transformer as V no load minus V full load upon V full load. If you multiply it by 100, you will get the percentage voltage regulation. Everybody just tell me, are you getting this idea clear in your mind? All the candidates who are watching me live, just quickly confirm whether you are getting this idea clear in your mind. Is it clear? Now if you see most of the old textbooks of machines, you may find a formula for voltage regulation as E2 minus V2 upon E2 multiplied by 100. That is the percentage. Now sometimes some people are saying that we are using the concept of regulation up and regulation down and all so many things, but that may not be correct for your examination purpose. Maybe for research and other purposes that may be good, but at your examination level you please try to understand that this is the old convention. This is simply about how you are going to establish anything. The old convention is, yes Hardik, how are you? Welcome to the session. That you represents the magnitude change in the secondary terminal voltage from no load to full load with respect to the no load value. That is why you are writing this formula. No big thing about this. But as far as gate examination is concerned, you have to use this formula. Okay, until and unless data is given otherwise, you will always represent the voltage regulation of a transformer with respect to the full load secondary voltage. Everybody getting this idea clear in your mind? Everybody is clear with that? Now I want to ask you that if you want to write the voltage regulation of the transformer, you tell me which equivalent circuit of the transformer you are supposed to use. We have three equivalent circuits of the transformer. Number one, equivalent circuit of the transformer. Second, first approximation equivalent circuit of the transformer. Two, second approximate equivalent circuit of the transformer. You must be knowing that we are going to use the second approximate equivalent circuit of the transformer. What is second approximate equivalent circuit of the transformer? Simply neglecting the shunt magnetizing branch. And this is going to be a very close approximation. Why? Because the I naught component of current is 2 to 5% of rated primary current. So there is no major discrepancy in the result. Hi Achyut, Arnav, how are you? Welcome to the session. Because I naught, that is the no load component of the current taken from the source, is going to be very, very small, 2 to 5% of the rated primary current. And there are two reasons for that. Number one, the core of the transformer is going to be highly, you can say, made of ferromagnetic material. So very small current is required to establish the flux in the core. Second thing is, transformer is going to be a static device. It is not like your induction motor, where induction and rotation, both the phenomena are happening. That is why I naught is going to be a very small value. So this approximation is going to be a good approximation. So how your second approximate equivalent circuit is going to look like? It is going to look like a simple RL series circuit. This is your input voltage, input supply voltage to the transformer. This is the secondary terminal voltage referred to the primary. This is going to be R equivalent, and this is going to be X equivalent, and this is going to be the current I. Everybody just tell me, are you getting this idea clear in your mind? This is the second approximation equivalent circuit for the transformer. Now I'm going to draw the phasor diagram. How you are going to draw the phasor diagram? By writing the KVL equation. V in is going to be V plus I, R equivalent plus JX equivalent. If you are taking a lagging load case, for a lagging load case, I am taking the voltage as the reference. Suppose the voltage is going to be the reference. Okay. And the current is going to be lagging in nature, because we are taking a lagging load, and this angle with which the current is lagging, the voltage is phi. Now in this terminal voltage, secondary terminal voltage, I am going to add the resistive and reactive drops so that you can get V in. This is going to be I R equivalent, and this is going to be J X equivalent I. Okay. And if you see the V in is going to be the summation of this, and you will get V in. I hope you are getting this idea. Now I want you to focus on the impedance triangle. This is going to be IR equivalent, and this is J times X equivalent I. So you can understand this. If this is O, this is A, this is B, this is C, then triangle ABC is going to be the impedance triangle of the transformer. If this is going to be the impedance angle of the transformer, now you can understand that if this is R equivalent, this is X equivalent, and this angle between Z equivalent and R equivalent we are defining as theta equivalent. So what is going to be this angle? This angle is going to be theta equivalent. Okay, is it clear? Now what is this angle? This angle is again going to be phi. So what is going to be this angle? This angle is going to be theta equivalent minus phi. Now if you take OC and you draw an arc which meets this line as C dash, and now you draw a perpendicular, and suppose this is F, and I ask you what is the voltage regulation, then you will say, sir, voltage regulation is going to be V no load minus V full load upon V full load. What is V no load? You tell me in this circuit. What is V no load? V no load is simply going to be V in, because no load means current is zero. If current is zero, this V is going to be equal to V in. Are you getting this idea clear in your mind? So this V no load we are writing as V in minus, suppose V load is terminal voltage V divided by V. This is the voltage regulation. What is V in? From this diagram, can you tell me what is V in? Yes, OC is going to be V in. So I am writing OC minus what is V? V is going to be OA. OA is going to be V. This is OA, and divided by OA we will get the voltage regulation. What is OC? Now OC, because this is an arc, so I am writing OC is equal to OC dash, and it is approximately equal to OF, because this distance is going to be very small. This distance is going to be very small. So you can write OC, that is V in, is equal to OC dash, or approximately equal to OF. Now what is OF? You see the triangle OCF. What is OF? OF is going to be OA plus AF. OC is going to be OA plus AF minus OA divided by OA. OA cancel. This becomes AF divided by OA. What is AF? You tell me. What is AF? This AF is going to be the projection of AC. What is AC? This is going to be IZ equivalent. This is IR equivalent. This is IX equivalent, J. So this is IZ equivalent. So the component of IZ equivalent on V axis will give you AF. So AF you can write as IZ equivalent cos of theta equivalent minus phi divided by what is OA? It is simply V. Now this I am going to take below this V. So you can write Z equivalent or theta equivalent minus phi divided by V upon I. What is V upon I? It is rated voltage and rated current, you can understand. So this V upon I is going to be Z base. Now apply the per unit. Yes, Rishabh Sarkar. Input voltage. Now apply the per unit concept. So you can write the voltage regulation as Z equivalent per unit cos theta equivalent minus phi. This is the final expression you are getting for the voltage regulation of the transformer. Now this is not a new equation you are getting for the voltage regulation of the transformer. There is one more general expression which is r per unit cos phi plus x per unit sin phi. This is the same equation, just it is being written in a different way. But you should be able to know both the equations, because whatever data is given, accordingly you can choose which particular expression you are going to use. I hope it is clear to all of you. Is it clear to everyone? Are you getting this idea clear in your mind? Suppose I am interested, suppose I am going with this equation. This is equation number 1, this is equation number 2. Both are same equations. The way of representation is different. Suppose I am interested in the maximum voltage regulation. What is voltage regulation? Z equivalent per unit cos theta equivalent minus phi. This value is going to be maximum when this value is going to be 1. When this value is going to become 1, cos theta equivalent minus phi will become 1 when theta equivalent minus phi is going to become 0. Or you can see the power factor angle is equal to the impedance angle of the transformer. And what is the value of this maximum voltage regulation? It is simply going to be Z equivalent per unit. Are you able to follow this? Are you able to follow this? Now listen very carefully. What is the important concept here? When I am writing this equation, whether this equation or this equation, these are approximate expressions for voltage regulation. Why approximate expression for voltage regulation? Because we have neglected this FC dash. This FC dash we have neglected. That is why we are getting the approximate voltage regulation, not the exact one. But when you say the maximum voltage regulation, if you draw the Phasor diagram, suppose this is your terminal voltage, this is your I, this is your V, and the drops are going to be like this. I R equivalent now IZ equivalent is going to be along V only. It means phi is equal to theta equivalent. This is the maximum voltage regulation condition. It means when you are talking about maximum voltage regulation, you are not taking any approximation, and that is why you are saying that voltage regulation maximum value, that is Z equivalent per unit, is the accurate value of maximum voltage regulation, not the approximate one. Everybody just tell me, are you getting this idea clear in your mind? At least say yes or no. Nobody is responding. If you're not getting, you can ask me number of times. But if you are getting, at least you can come out of your shell, and when I'm asking whether you are getting this or not, you can simply say yes sir, no sir, this is my doubt, why it is so, why it is not like that. But if you're not responding, it is very difficult for me to carry forward the session. It means you're not interested in the session and I should stop. If you want me to stop, I will stop, no problem. But you have to tell me what do you want. Achyut. Now listen, when we are saying maximum voltage regulation, you have to understand voltage regulation is nothing but the drop in the voltage at the secondary of the transformer. Definitely this drop is going to be maximum when a lagging load is connected. It means maximum voltage regulation you will always get when the load is lagging in nature. Now suppose you want to know the zero voltage regulation. If you want the voltage regulation to be zero, what is the condition? What is the expression for voltage regulation? Z equivalent per unit cos theta equivalent minus phi. You are saying you want to make this value equal to 0. What is the meaning of making the voltage regulation 0? You want to say if the load is changed from no load to full load, the change in terminal voltage at the secondary should be 0. Are you getting this? Are you getting this or not? You want V is equal to V in. This is the condition for zero voltage regulation. It means even though there is some drop in the voltage at the secondary, you want this drop to be compensated. Now, how you are going to compensate that drop? Only and only when the load is going to be leading in nature. So, zero voltage regulation condition is only possible when the load is going to be leading. Are you getting this idea clear in your mind? Is it clear? Not getting? When this value is going to be 0, when theta equivalent minus phi is going to be equal to 90 degree, or you can say phi is equal to theta equivalent minus 90 degree. But you have to remember this you have found by using the formula for lagging load. For leading load, phi must be changed with minus phi. It means for leading load condition, you are getting zero voltage regulation. So phi you will be getting minus of theta equivalent minus 90, or you can say 90 minus theta equivalent. Same condition that we have achieved if you discuss the short transmission line voltage regulation. I hope you are getting this. Now when you are going to get the minimum voltage regulation, when you are going to get the minimum voltage regulation, the minimum voltage regulation you will be getting again for the leading load condition when you are getting negative value of voltage regulation. So again phi you have to change with minus phi. Are you getting this? So what is the voltage regulation you are writing? Z equivalent per unit cos of theta equivalent plus phi. For the leading case you have to change phi with minus phi. And if you want the minimum value of voltage regulation, this is going to come at phi is equal to minus 90 degree. You know from the discussion, if you see this expression for voltage regulation, very easily you can find what is the minimum value of voltage regulation. For leading power factor, it is going to occur when phi is equal to 90 or minus 90. Are you getting this? Now you were putting phi is equal to minus 90 for the old expression, when here it was a minus sign. So you will be putting plus sign. Are you getting this? All these small changes you should be able to do. So now if you write the voltage regulation minimum value, this is going to be Z equivalent per unit cos of, this is going to be theta equivalent plus 90. And this is going to be minus Z equivalent per unit sine theta equivalent. What is Z equivalent per unit sine theta equivalent? It is simply going to be minus X equivalent per unit. Now if you draw the variation of, yes, mass plus Welcome to the session. How are you, beta? This is the power factor angle and this is the voltage regulation. And if you see the variation at phi is equal to 0, getting the voltage regulation as R per unit at phi is equal to 90 degree for the lagging load, getting the voltage regulation as X per unit. In between phi and 90, one value it is going to be maximum for phi is equal to theta equivalent. And the variation is going to be something like this. What is the value of this? This point is Z equivalent per unit. This is the maximum value of voltage regulation. Voltage regulation is going to be 0 for phi is equal to 90 minus theta equivalent for leading load conditions. So the curve is going to pass here. And if you put phi is equal to minus 90, we will be getting the voltage regulation is minus X per unit. So this is the complete variation of the voltage regulation for both lagging and leading load condition. One important conclusion you can draw out of this discussion is that for all the lagging load condition, the voltage regulation is always going to be more than R per unit, and for all the leading load conditions, you can say voltage regulation is going to be less than R per unit. Everybody is telling. So if I give you the value of voltage regulation and the per unit equivalent resistance of the transformer, can you tell me whether the load is lagging or leading? And I can guess that this year 2021 you will be getting a question on this. I do not give guarantee because I am not selling toothpaste, but this is highly probable. I hope you are getting my point. Everybody just confirm yes or no. Are you getting this idea clear in your mind? No one. Are you getting this? If my image is hiding the figure, I am removing my image. You can see the complete diagram. Now you tell me, if you want to reduce the voltage regulation, you want to increase the voltage regulation for a good transformer, or you want to increase the voltage regulation? You tell me, what is your choice? Whatever you say, that I will follow. For a good transformer, it must have a low value of voltage regulation or a high value of voltage regulation. You should tell me. The variation at the secondary terminal voltage from no load to full load, it is going to be high or less. Definitely it should be a less value, then only you are going to get a good transformer. Now for voltage regulation to be a smaller value, definitely leakage flux should be minimum. Leakage flux should be reduced. How you are going to reduce the leakage flux? Number one, let us talk about core type transformers. Core type transformer, what you are doing? First, you are using concentric windings. You know concentric windings? If this is your transformer, it is not like you are going to place primary winding on one limb and secondary winding on another limb. No. Half of the low voltage winding you are going to place at this limb, and half of the low voltage winding you are going to place at this limb. It is concentric windings around the same core. Now over this, half of the high voltage winding you are going to place on this limb, and half of the high voltage winding we are going to place at this limb. Generally, high voltage winding we are going to keep at the outer layer, and low voltage winding we are going to keep near to the core, simply because of less insulation requirement. Insulation requirement is less. The only reason. Second change in the design of the transformer, if you're talking about the core type transformer, I am giving you two types of transformer construction, and you tell me which type you are going to prefer. You have to tell me which type of core construction you are going to prefer for low value of voltage regulation or less value of leakage flux. You tell me. You are going to decide because you are manufacturing the transformer. If this is your winding, which of these two constructions you are going to prefer? If you see here, the leakage flux is going to be like this. If you see the leakage flux here, phi L1, this is phi L2. You tell me if this is A and this is B, in which leakage flux is going to be more? What is your choice? Definitely leakage flux is going to be less in this case, and it is going to be a higher value for this case. If you see this case, height upon width ratio, height upon width ratio. Sorry, I have written wrong. Let me just correct myself. This is going to be a higher leakage flux, and this is going to be a less leakage flux. Why? Because here the leakage flux has to travel a smaller air gap. So a smaller reluctance it is facing, and reluctance or air gap is going to be small. So leakage flux is going to be more for the case A. And here the air gap length which the flux has to travel, or the reluctance, is going to be high. So leakage flux is going to be less. If you see the ratio of height and width, the height is going to be less and width is going to be high. So height to width ratio is going to be smaller one for this transformer. If you see the height to width ratio for this transformer, height is more and width is less. So height to width ratio is going to be more. So now you can say for less voltage regulation, leakage flux should be less, or you can say height to width ratio of the core type transformer should be, yes, Achyut, you are right. In B case, the flux is going to be less. The height to width ratio of the core should be very, very high. Are you getting this idea clear in your mind? Tell me yes or no. Everyone. Similarly, if you see the shell type transformer, we are using the sandwich windings or interleaved windings. Interleaved winding means high voltage and low voltage windings, they are placed alternately. Everybody just tell me, are you getting this idea clear in your mind? See, you are not responding. If you are not responding, it will become very difficult for me to continue the session. You have to tell me. Let us now quickly talk about the transformer efficiency. Very less time we are having. Transformer efficiency. How you are going to define the transformer efficiency, you tell me. Efficiency we are defining as output power upon input power. Multiply by 100, you will get the efficiency. Now you tell me what you will prefer. You want to write the transformer efficiency with respect to output power or input power. If I am saying it is a 300 kVA transformer, you tell me what is this value of the volt amperes or the power given. This is output or input, you tell me. You apply your logic. Everything is not going to be mentioned in the book. You have to apply your logic. If this is your transformer and I am saying this is the nameplate rating of the transformer, I am writing 300 kVA. What is the meaning of this 300 kVA? The meaning of this 300 kVA is that this much power is going to be. TNR Lucky is saying please solve problems. For problems, let me tell you, I think you are not aware. We are having impulse channel, impulse Gradeup gate channel on YouTube. You can follow it today itself, and we are doing problems here. We are taking problems here. Very good quality problems on machines and power system I have taken. If you want, you can follow those sessions. They are available in the playlist. I think you are not aware with that. Already we are taking problems there. Anyways, and let me tell you the session detail. 12 p.m. in the afternoon. Okay, almost nine sessions are available. You can follow that. It simply means that if you are going to connect this load here, you are going to connect, then how much current it is going to draw. Are you getting this? It means we are interested to write the transformer efficiency with respect to the output power. So you can write it as P output upon P output plus losses. Let us see the transformer losses. You tell me what are the possible losses in the transformer. There are going to be, let me just hide my image. There are going to be two types of losses. Core losses, because transformer is a static device, and copper losses. Core losses, you know that we can define as hysteresis losses, and this is eddy current losses. Okay. Hysteresis losses, you know, we are defining as they are being directly proportional to frequency and maximum flux density raised to the power n, where n is the Steinmetz constant, and generally whose value is taken as 1.6. If you see the eddy current losses, they are directly proportional to the square of frequency, Bm square and T square. What is T? T is the thickness of insulation. Thickness of insulation. If you see the copper losses, these are the I square R losses, and they are defined as variable losses. Core losses we are defining as constant losses. What is the meaning of constant losses? Actually, they are not constant. Some variation is there, but still for the sake of our convenience, we are saying We find the constant losses found at no load and treated as constant losses from no load to full load. We are just making our life easy. Otherwise, it is going to be very difficult. Are you able to follow this? Now, in general, now if I have to write the transformer efficiency for full load condition, how I am going to write the transformer efficiency for full load? S is going to be the output power multiplied by cos phi, because we are interested in the real power. We always define efficiency with respect to real power, because you can only put the real power to the useful work, not the reactive power. So this is going to be S cos phi divided by S cos phi plus PC. What is PC? Core losses, hysteresis and eddy current losses, plus this is going to be PCUFL. What is PCUFL? This is full load copper losses. It is going to be core losses. Multiply by 100 and you will get the efficiency at full load. You get the efficiency at full load. Are you getting this idea clear in your mind or not? Tell me yes or no. Now, suppose I am not interested in the full load, any general load I am writing. So I am writing the efficiency as VI cos phi plus I square R equivalent plus PC. What is PC? Core losses. What is I square R equivalent? This is the total copper losses, you can understand. And you can multiply by 100 if you want it in the percentage. Now efficiency is going to be maximum in two cases. Number one, if load is constant, if the current that the load is drawing, it is constant, then maximum efficiency you will be getting when cos phi is going to be 1. What is the efficiency? You have to maximize the output. If you maximize the output, losses are automatically going to be minimized. Yes or no? What is power output? So this is VI cos phi. You are saying I is constant, V is constant. So what you can change? You can make cos phi maximum. What is the maximum value of cos phi? This is 1. It means unity power factor is the condition. If the load is constant, if the load current is constant, you will be getting the maximum efficiency. If power factor is constant, you will be getting the maximum efficiency by using this procedure. How you can write the efficiency? You can write as V cos phi, cos phi is constant, as V cos phi plus I R equivalent plus PC upon R. Now this thing you want maximum, so this this thing should be minimum. So just differentiate this value with respect to I. So if you differentiate with respect to I, you will get 0 plus R equivalent minus PC upon I square is equal to 0. So you will be getting PC is equal to I square R equivalent, which is P copper. It means constant losses are equal to variable losses. Everybody just tell me, are you getting this idea clear in your mind? Now what is PCU? PCU you are writing as I square R equivalent. What is I? Suppose it is X times the full load current. So you can write it as X square I full load R equivalent. So can I write it as X square PCUFL? Because this is nothing but PCUFL full load copper loss. So you can write PC is going to be X square PCUFL, or you can find the loading condition at which the efficiency is going to be maximum by using this formula. Everybody just tell me, are you getting this idea clear in your mind? Clear? And can you tell me what is the maximum value of this efficiency? Can you tell me what is the maximum value of this efficiency? Yes, this is going to be xs cos phi upon xs cos phi plus 2pc, because core losses and copper losses are going to be same. And what is x? X is under root pc upon pcu fl. I hope you must be getting some idea about that. Now we are running short of time. I wanted to discuss open circuit short circuit test also. I wanted to discuss all day efficiency also. I wanted to discuss the separation of hysteresis and eddy current losses also. But time is less, and one more thing, the response of the students is very weak. If this response I am getting, I cannot be motivated to give my 100%. Okay. So you have to be regular in the class. Okay. If you are not taking the classes seriously, then I also have to rethink. This is an important question. Anyways, I'm just concluding now. We are running short of time. And before I conclude, let me just brief you that if still you are in a dilemma that how you should prepare for the GATE 2021 examination, how you should revise, then Gradeup has opened the window for you till 30th of January 2021. You can access the Gear Up and Rank Up classes. In Gear Up we have covered theory, and Rank Up we have covered numericals. And this is not that you have to take the separate subscription. In the same subscription, just one subscription if you take, you will be getting for your time validity the classes for Vision 2022, Rank Up and Gear Up. This is how you can have the best way of revising for 2021 and still giving a chance to 2022. These are the star faculties in the electrical department who are going to help you in the next preparation cycle. These are the results we have produced over the years 18, 19, 20. We have brought the best of the students into the final result, and you can see 2020 has been a landmark year where 60 plus Gradeup students have achieved under top 100 rank. This is about the Gradeup Super subscription that I was telling you. Suppose you are going for Vision 2022, then you don't need a separate subscription. In just one subscription, you will be getting access to all the structured live courses on the Gradeup platform, and you will be getting access to the online mock test designed by the toppers based on the latest exam pattern. For any further clarification, you can contact this number. This is all from my side. Thank you so much for joining me in this session. I know that less students have joined me in this session, but definitely I am sure whosoever is following me, definitely you must have got some value addition. If you have any doubt regarding whatever I have discussed and you want to discuss something, you want to ask something, you can ask your questions in the comment section of this video. Even if you are watching it offline, I will be more than happy to answer your doubts about the voltage regulation and efficiency of transformer. And the best way is you can go to the Gradeup app. You can download Gradeup app, where there is going to be a lot more authentic stuff for making your preparation a perfect preparation for the given competitive nature of the examination. So thank you so much friends for joining me in this session. I hope that you are going to follow me again. Tomorrow also we are going to discuss. Tomorrow I will be discussing auto transformers and three-phase transformers, 9 p.m. in the evening. So if you want, you can join me. Also, tomorrow 12 p.m. in the afternoon on the Impulse channel, that is the new channel which is a dedicated channel for electrical and electronics. I will be discussing the same topic questions. One candidate, I don't remember his name, CNR Lucky. If you are listening to me, CNR Lucky, you can follow the questions based on auto transformer and three-phase transformer in tomorrow 12 p.m. session on the Impulse new Gradeup channel. That is a bilingual Hindi-English channel. And in the evening 9 p.m. I will be discussing the theoretical backup for the same, that is auto transformer and three-phase transformers. So thank you so much, friends, for joining me in this session. Take care of yourself. Practice smart, score better, go Gradeup. Thank you so much. Thank you.